what's the infinite sum from 0 to infinity of minus 1 to the power n times 1 over 3n plus 1? So this infinite series, in fact, so when n is equal to 0, we have 1 times 1. n equal to 1, we have minus 1 over 4 and plus 1 over 7. Of course, minus 1 over 10 and so on and so forth. Right? So first of all, this is a alternating series, a Leibniz type series. Of course, this one is convergent. But convergent to what? So we're going to first construct a generating function s of x called infinite sum from 0 to infinity of negative 1 to the power of n times x to the power of 3n plus 1 over 3n plus 1. So the derivative of s of x is equal to infinite sum from 0 to infinity of minus 1 to the power of n times 3n plus 1 times 1 over 3n plus 1 times x to the power of 3n. Right, that's the reason we need the power of 3n plus 1, just to cancel out with the denominator. And the legitimacy of differentiating term by term is because, first of all, so after we differentiate our new series, it is, of course, if we restrict x in between negative 1 and 1, then it is, of course, convergent, right? Obviously, because this is a geometric sequence. Because the first term is what? First term is 1, right? Second term is minus x cubed. And then we have a plus x to the power of 6 minus x to the power of 9, and so on and so forth. A common ratio is just minus x cubed. So this is in fact 1 over 1 plus x cubed. Right? Like I said, first of all, our new series is, of course, convergent within this open interval. Right? Then, of course, it is uniform, because it's, so the radius, right? Convergent radius is just 1, right? Easy. Right? Then 0, negative 1, 1. Right? In this open interval, it is convergent. Then we can easily see that, is it convergent at then if we just fix x in this open interval, for example, we fix x to be in here, right? So that we can draw a closed interval inside this open interval containing x, so that even though the series is not uniformly convergent over this open interval, but it is uniformly convergent over this closed interval inside this open interval, and x is within this closed interval. So this is really uniformly convergent inside any closed interval within this open interval. Right? So this is really legitimate. And of course, the original series, right? Original series, is it at least convergent at one point in this open interval? Yes, of course. right? So after we differentiate here, each term here is, of course, continuous, right, in this open interval. So it is really legitimate. Then all I have to do is to check what's the value of S of 0. So obviously it's 0. So S of x minus S of 0, it is the definite integral from 0 to x. Right, maybe treating x as a constant. And then we can turn this x into t, right? Variable of t, dt, 1 plus t cubed. Right, maybe treat it as a changing upper bound integral. Right, S0 happens to be 0. So this is in fact S of x, right? S of x. So again, according to Abel's second theorem, and we're told that if I'm looking at this series, right? If this series is convergent at its, for example, right-hand side edge, and again, this time the radius of this series, right? So this is easily just 1. It's easily verifiable. 0, negative 1, 1. So it's really convergent at the right-hand side edge, meaning when x is equal to 1, we have this original series. Like I said, Leibniz alternating type of series, of course, convergent, right? And Abel's second theorem tells us that if that's the case, then our S of x, right, this function, right, has to be continuous right at this point, right, from the left-hand side, right, this point from the left-hand side. Now, to write it down, S of 1, right, that's the meaning of continuous, meaning the functional value equal to the limit. So S of 1 equals the limit x approaching 1 from left-hand side, right? Left-hand side of S of x. S of x is this, right? 0 to x dt, 1 plus t cubed. Right? So like I said, it says, Abel's second theorem says, it is continuous from the left-hand side, right? So meaning the limit value from the left-hand side really equals to the functional value at point 1. So equal to the, when x is equal to 1, right? X is equal to 1. So really equal to 0 to 1 dt, 1 plus t cubed. Right? That's where the legitimacy is. Then we can just quickly work out the integrand, right? The integrand seems to be antiderivatable because it's a rational function. Right? All we have to do is to split it into a sum of several terms that easily have antiderivative. So first of all, 1 plus t squared is equal to 1 minus negative t to the power of 3. And then we have the formula of 1 minus t times 1 squared times 1 times minus t plus minus t squared. That's t squared. Right, with a plus here. Right, then we have to just, in order to split it up, we have to determine the constant a over 1 plus t plus bt plus c over maybe t squared minus t plus 1. All right? since we have power degree of 2, therefore we have to write bt plus c instead of just a constant. So in that way we have to determine the constants. So first of all, t squared term, right? Constant, we have a, and then we have b. So we have a plus b. Right? A plus b as t squared, because we know that in the end they should add up to just 1. So meaning that tells me a plus b is equal to 0, right? Times t squared, then plus t term, we have minus a, we also have b, also have c, b plus c minus a times t. Constant term, we have a, we have c, a, c equal to 1. So that tells us that a plus b has to equal to 0 no matter what. And b plus c minus a has to equal to 0 no matter what t is. Right? Also, a plus c has to equal to 1. So right now we have a plus b equals 0, b plus c minus a equals 0, a plus c equals 1. So which means b is equal to minus a. Right? Using this and that, now we have b plus c plus b, 2b plus c equals 0. Right? This expression gives us minus b plus c equal 1. Right? So this minus that, we have 3b, c is gone, we have minus 1. B should be equal to minus 1/3. Right, so A is equal to 1/3. C is equal to 1 plus B. 1 plus B. 2/3. Right, no problem. So common denominator, common factor is what is 1/3. Perhaps we can just factor out 1/3. So right now we have. So 1 over 1 plus t cubed is equal to, like I said, factor out 1/3. 1/3 bracket. And after, so a is equal to this. So then we have 1 over 1 plus t plus bt plus c, 1/3 factored out, bt plus c. 2 minus t over t squared minus t plus 1. Yes. Okay. Right. So that means all we have to do is to integrate this from 0 to 1. Right. Then we can work out s of 1, our desired series. So right now, 1 over t is easy to integrate, right? Log of 1 plus t. How about this? If we differentiate the bottom, if we want to say, okay, maybe it's log of t squared minus t plus 1. How about we use the chain rule to verify it? Differentiate the bottom, we have twice of t minus 1. But in fact, we have minus t plus 2 here. So maybe I just multiply by 2 on top and divide and multiply by half, right? Then I have maybe 4 minus 2t. But I want to have 2t minus 1, right? 2t minus 1, maybe factor out minus sign. Factor out minus sign, then I have maybe 2t, maybe 2t minus 4, right? 2t minus 4. 2t minus 4. Minus 4 can be split into minus 1 and minus 3. Right, so that's the plan. So that is so, which means I'm just gonna leave this aside and focus on this one. Right. So 2 minus t over t squared minus t plus 1, that is equal to, like I said, first multiply by half, then times half on the top, right? So t squared minus t plus 1. Of course, factor out the minus sign. Minus sign. We have bracket, we have this time t minus 2. T minus 2 altogether times 2. 2t minus 4. Like I said, minus 4 can be written into minus 1 minus 3. So that way I can use my chain rule to verify. So it becomes 2t minus 1, 2t minus 1, yes. So I can use log of t squared minus t plus 1 as my antiderivative. So I can just split this and that. Right? So that should be equal to, again, negative half times, like I said, 2t minus 1 over t squared minus t plus 1. Again, then I have minus 3 over t squared minus t plus 1. I can split them up. So that way. Right. So I'm good with this one. This one is safe, right? This one is okay, easy to solve. How about this one? What's its antiderivative? Looks like maybe I can do some manipulation and turn it into maybe some variable square plus 1. Then its antiderivative can be arctangent. Right? Maybe I can just complete the square. So now that we can see that this one is easy to deal with, and this one I've just written it into like this. Right? But this can be split into this and that. But this is also easy to deal with because it's just find its antiderivative, it's just log of the bottom, right? Because chain rule, so differentiate bottom gives me the top. So this is easy. So then I just have to focus on this one. Right? So this one I want to turn it into the derivative of arctangent. So how do I do that? So like I said, I can just maybe complete a square. So I have 3 over t squared minus t plus 1. That is equal to 3 over t minus half square, right? Because when I expand the square, I have t squared minus t plus 1/4, then minus 1/4, then plus 1. So plus 3 over 4. Right? So then I'm going to factor out the 3 over 4. Right? Then in front of that, I have to multiply its reciprocal, 4 over 3. Right? But 4 over 3, I want to combine it into the square. Right? So that becomes the square root of 3 and 2. Right? 2 over square root of 3 times t minus half. Right? Altogether, square. So this just turned into 1. Right, this time somehow I have some whole entity square plus 1. Right, this should be the derivative of arctangent. Right. So 3 over 4 minus 3, 4. Right, so 3 over, divided by 3 over 4 times 3 over 4. So this 3 and 3 just cancels out. Multiply by 4. 4. So 4 sits on top. So 4 is gone. Right? This time it's sitting on top. So I'm treating this as a whole entity. Right? So I'm going to use the arctangent of of course, I multiply by 4 in front. Arctangent of the whole thing. 2 over square root of 3 times t minus half. And use the chain rule. Right? because we're going to have a 2 over square root of 3 coming out. So multiply by its reciprocal. So multiply by square root of 3 over 2. Now I've broken the original integrand into 3 parts, where each part it's obvious to see its antiderivative, right? So first one. So that means my desired definite integral should be equal to, first of all, 1/3. Right? The antiderivative of this is just log of 1 plus t. I'm going to evaluate it from 0 to 1. Okay? Then we have minus half of, like I said, log of the bottom, right? T squared minus t plus 1, evaluated from 0 to 1, right? Like I said, chain rule, differentiate inside, twice of t minus 1, twice of t minus 1, exactly what we have here. Right, so now this one, antiderivative, like I said, happens to be this, right? So if we just use this to multiply of course, the negative sign in front. Negative sign becomes plus. Multiply by half. Right, multiply by half. So we have just square root of 3 in front. Right? Plus square root of 3. Arc tangent of 2 over square root of 3 times t minus half. So evaluate it from also 0 to 1. Right, let's see what happens. So this one is easy. This one is log 2. Because log 1 is already 0. Log 2. This one is it 1 plus log 1 is 0. And also log 1. Also 0, so this term is gone. How about this? Arc tangent, if we substitute ones. Half, 2 over the square root of 3 times half. Arc tangent of 1 over square root of 3. I believe that's pi over 3. No, pi over 6. So what is square root of 3 pi over 6? Yes, pi over 6. Right? So 0 substitute into it. Negative 1 over 3 square root of 3. Negative square root of 3. Please. Negative pi over 6, right? So becomes plus. Right, so pi over 3. Altogether, pi over 3. Pi over 3 times the square root of 3. Pi over square root of 3.